Hey folks, sorry to be late. Thanks everybody for joining. And hello to colleagues in APAC. Hello, Tyler. I'm just going to start by giving a quick debrief of the OCP Global Summit that we had in San Jose last month. Excuse me. Saw a lot of folks from our sustainability project there, and it's always a good time for us to sort of take stock of what we've accomplished throughout the year, check in with each of the work streams on what they're doing and how we can work across those work streams and to make plans for the coming year. Those of you who have not been to the Global Summit before, it keeps getting bigger every year. I think we're on the verge of outgrowing the San Jose Convention Center, um, which is fantastic because it demonstrates the appetite and the willingness in our industry to collaborate on open standards generally in the digital infrastructure industry, and more specifically on sustainability. I was really pleased with how much energy there was around sustainability and how much participation we had this year. Let me quickly bring up a slide and I'll give you a little bit more of a detailed debrief here. Hang on just a sec. This is the one. So first of all, I just wanted to highlight the cross work stream meetings that we were able to hold, which were especially useful to talk about the ways in which our various work streams, um, the work is supporting each other. It's complementary. So we had meetings with among Carbon Disclosure Group, Circularity Group, the working group working on PCR development, and had those combined with other working groups, including the Carbon Disclosure Working Group, which is important because the format that they're developing for a standardized means of carbon disclosure needs to reflect all of the new work happening in each of those other areas. And there was great discussions on sort of where that carbon disclosure group can go from here based on all of the new outputs from those other working groups. We had great presentations from all workstream topics, including power telemetry, new spec that they're developing, efficiency metrics, and then we also got to talk about water efficiency from several angles. And as I said, we had a full day track on sustainability. So it's really nice at each of these summits and each of the regional summits in Europe to have a day dedicated to sharing new research and ideas on sustainability, um, and get sort of all in one day a great shot of new technologies, new analysis, and new research that's being done on how we can move forward from where we are. So as I referenced, we did have a presentation from the OCP's Carbon Disclosure Group, and there's a new OCP spec from them, which you can see pictured in the lower left there up on the big screen. So a solution that is on the OCP marketplace that has been accompanied by this disclosure form can earn that tag. And it's a way to indicate to the broader market that the work has been done to measure and report on the embodied carbon of whatever that solution is. Um, we heard about a pilot project for emissions-free backup power run by the Net Zero Innovation Hub, and Google and Microsoft, among many others, Iron Mountain, Data4. Um, which is exciting because I think that this is something that there's a lot of discussion about in the industry, and we're going to hear one angle on this in a moment from Tyler, is to figure out how can we bring our own power such that we obviate constraints at the grid? How can that on-site power help us advance sustainability, but also allow us to find new capabilities in terms of grid interaction, which lets us further sort of automate loads to maximize cost and carbon, and how can we get around air quality permits, which have become a top limiting factor, top three limiting factor in our ability to build new facilities. One other thing I wanted to call out is the new work stream to examine procedures and develop product category rules for CIT equipment. This is a funded activity through by Microsoft, Google, and Meta, administered by Fraunhofer. And this is sort of the fundamental building block that we need for better standardization around embodied carbon measurement and reporting. So it's really nice to have that work happening in OCP. I think it's the perfect venue, this open setting for us to collaborate across the industry. Um, and look forward to hearing more from them in successive summits, hopefully um, in Barcelona, I believe, is where it's going to be in Europe next spring, and then hear more in San Jose next fall. Any observations from anyone on the phone or any questions on the global summit and what was covered? Well, then, with that, I would like to introduce our guest speaker for the month. So Tyler Andrews is a VP of Business Development at Ekion Technologies. He has 15 years of experience in advanced vehicle and industrial development programs, including power generation and energy storage. As the vice president at Ekion, he's focused on the development of ultra-high power battery chemistries, utilizing novel anode materials that enhance safety, cycle life, and TCO over current technology. And I swear I just memorized this all. I'm not reading. At Ekion, Tyler is leading global business development efforts to commercialize those battery solutions in high performance and heavy duty industrial applications, including data centers. He is a natural scientist by background, which makes me feel a lot of sympathy for him as a biology major myself and an undergraduate and an MBA. So Tyler has some meta-analysis to share with us around these advanced battery technologies, particularly within the data center context. So with that, welcome, Tyler, and thanks for joining us.
Yeah, I appreciate it. Can you hear me okay?
Yeah,
Excellent, excellent. All right, let me get my screen shared real quick here.
is it working for you?
Yeah, I think does that come through?
I think it's coming. Yes, we got it.
Excellent. Awesome. All right. Well, I appreciate everyone having me on, and so it's my first time actually joining the OCP group. I've been working in the energy space for some time now, and have had a huge following for AI and curiosity to see where this is going to continue to trend towards the future. Obviously, I think that's going to be a very positive direction, but also following a lot of the challenges that are presented in AI, especially as we look at kind of that energy story. And in fact, our story at Ekion started on the AI side with a really simple question from an investor and a consultant in the AI space, where they said, we're looking at trying to create a power-based solution for energy storage, specifically at the facility level. And they said, how if you guys are power focused tech chemistries, like how small can you get that? And that led to a kind of a twisted road of research at rack, UPS, and ESS storage solutions, and has really kind of led to this path where we are today, where I'm presenting to you, to everyone here. So um, looking forward to diving in. As we go through this, if there are any questions, please feel free to stop me. I will be the first to say I'm not an AI expert in all of the terminology and compute and different things that we run into. It's obviously a huge industry. So if there's anything I misinterpret or misspeak on, please forgive me. But I think it should be pretty easy to follow. Um, oh, sorry, I lost my screen here. There we are. All right. So I want to start off specifically on the kind of this energy chain for AI compute, and you know I think it was recently said, actually, I think it was earlier this week or late last week, where Satya Nadella, the Microsoft CEO, said, our biggest issue that we're having now is not compute, it's power. And as we look at this line below here at the bottom of the screen where it says supply demand, I think that becomes pretty evident that as we move closer to the edge, and in this case, the edge is that IT rack infrastructure, um, the more dynamic our load demand becomes. And and this creates a lot of challenges, right? This is basically the inverse of the economic bullwhip effect. And to put it lightly, our grid infrastructure, our power generation is not really equipped to handle this, at least at the loads that we're asking it to respond to. And, these power swings and these frequencies create a risk of grid instability. It creates issues with inertia and resonance, both at the generation and transmission infrastructure, and can contribute to the early onset of mechanical failures and possible blackouts. And there's some really interesting data out there. You'll notice at the bottom of these slides, I have some references. And so, if you're wondering where I'm pulling some of these resources from, please feel free to click on those links. Some of them are actually contributed from previous slides from the OCP group, and others are white papers that are out there in the ether. But the point is how are we going to begin affecting this in a positive way? And Ekion Technologies, as a company that is focused on energy storage solutions, obviously one of the first things that we look at is, well, is there a way for battery technology to step in and help mitigate some of these risks? And you know, as we look at this, the upper supply demand curve versus the lower, one thing that we've noticed in our research and is also supported by many energy studies out there is the fact that we have rack level, UPS level, and ESS level solutions that all when combined can really work to flatten this curve and create a much more efficient compute environment that has a dramatic impact on energy savings, as well as reducing the strain on grid. And a lot of my focus is obviously there's a sustainability aspect to all of this, but businesses still tend to make money or tend to make decisions driven by metrics based on profitability. And one of the things that I really like about this story is that it aligns with both. It has a very sustainable aspect to it, but also has a profit-driven aspect for operators that looks very attractive. A huge portion of this data was actually driven by a white paper that was created by Microsoft, OpenAI, and NVIDIA about power stabilization for AI training. And in this, they really look at three models. That's software-only mitigation, GPU power smoothing, and rack-level energy storage. Don't have time to get into all three of those today, but again, the link is below if you want to check it out. What I do like is that table one, where they kind of show, hey, what's the reliability, performance, energy costs, all these different metrics that they use to evaluate this. And rack energy storage was really attractive in the majority of these. Very high reliability, high performance. Um, the energy aspect of it to implement it was low. Um, the ability to meet spec, all of those were very, very strong. And you can see the performance results of that on the table immediately above it, where it shows this kind of power smoothing effect where we create a better nominal position. And the best way I can attribute this is it's almost like a water tower. And if you turn on your faucet, you don't want latency. You want immediate response. You want that. Ideally, you want hot water immediately. We know sometimes we have to wait on that, but at the very least, you want immediate flow. And we're looking at the same thing in this high frequency environment that's happening in milliseconds at the GPU level. And whenever we flip that switch on, we want that compute to be immediate. We want that energy to be immediately there. And that becomes incredibly challenging. And so energy storage is a really nice way to work with that. So as we begin to say, all right, well, how do we define this problem? What does it look like today? One of the first things we want to call out is, there is obviously battery energy storage solutions at the rack level today in BBUs. A lot of that is based around NMC and NCA chemistries. Um, One of the challenges that as we look at scaling this into really high power BBU solutions, in those 72 plus kilowatt hour shelves, um, is the risk that these chemistries are now beginning to get into a stressed environment where we create dendrites, we degrade the SEI layer, we shorten the battery life, and we create a potential risk for thermal runaway. And so there's only so far we can push some of these without creating kind of an adverse risk on the opposite side for safety and life and thermal regulation and all those different things. Um, so our concept that we looked at is kind of twofold. One, how do we achieve a power dense rack solution that can hit around 150 kilowatts to start in a kind of an HPR V1 um, kind of setup. And so looking at a CBU, which is a capacitive style battery unit, and a BBU, leveraging our XNO chemistry, which is a mixed niobium oxide based chemistry, we can achieve 75 kilowatts at the capacitive side and 75 kilowatts at the battery side combined for 150 kilowatt. In utilizing only a 3U setup on an ORV3 rack. So the nice part about this is that we could go higher, and there's already formats of getting out there as we look at HPRV2, HPRV4. These changes kind of the width, the depth. We can fit more cells or a more optimal cell format to get into that 200 plus kilowatt solution. Um, in this concept, we have a really good dynamic of safety and life. And then the other part is depending on how we configure racks, we can do the low voltage 48 volt setup plus minus 40 or 800 volt configurations. And so the whole part here is flexibility and power and being able to do this at a high level, um, being flexible in our nature, and then leveraging the benefits of these two technologies to create both that instant power that's required at the GPU level, and that's just supplied by the capacitive unit, and then that longer sustained power by the battery backup unit. This is really well illustrated here in that graphic up to the top right, where we talk about kind of that peak load support, where the BB or where that capacitive unit is helping in the microsecond environment, and and ensuring that that compute efficiency is immediate in there as soon as that power is requested, and then supported in longer term by the battery backup unit. Um, and some of the articles that we have linked below, they show that these compute efficiencies are quite substantial. It's a 20 to 30% efficiency gain in energy. Um, really focusing on three areas, and that's power loading, which is a bit like that water tower analogy that I had earlier, where we don't have that latency, that power and that pressure um, is there immediate for the for compute to use. Um, this again leads to better compute efficiency, and then heat generation. And whenever you look at all of these together, it has a synergistic effect of helping one another. The supercapacitor helps the battery supports the long-term power. This is tremendous for the power supply unit and backup the energy chain as we go through UPS, transformers, rectifiers, inverters, all of the above. We're asking everything to do a little bit less, and we're asking it to do in a better operational efficiency than what it would normally be asked to do without these systems in place. So looking at the next stage of that, we already talked about rack, now moving to that next stage of UPS, because I think as we look at some of the high voltage DC architectures that are being evaluated, this is super important to say, well, what does this look like in future systems over the next, 2, 3, 4, 5 years, however long it takes. And one of the biggest challenges that became immediately apparent is a lot of UPS solutions are based on legacy lead acid systems. These are tried and true. They're they were fine for what we did then. They're not really tailored well for what we're asking from AI today. Um, and so these solutions create or require about 50 to 70% more floor space. It's 50 to 60% more weight, and there's pretty frequent battery replacements between that 3 to 5 year range, even compared to very basic lithium ion solutions. So these aren't even like the premium options out there on the market. And so that's a problem. And as we know, like space is is not a minor thing in any data center. All of this is precious real estate that can be used towards other purposes. Um, as we look towards transitioning into the high voltage disaggregated systems, though, there's really a tremendous opportunity to move towards that high power UPS solution. Um, just the HVDC alone creates about a 4% system efficiency increase, and that's just because you're not going through, um, the that that um, the rectification process and everything. But in addition to this, as we look at these highly efficient chemistries, there's more to be gained there as well. And this is due to low resistance, low heat, in the battery systems, efficient UPS design, all of the above come into a really effective unit. And so what we did is we kind of asked the question is like, how much power can we generate in kind of a minimum viable product model? Thinking that almost put it into power per square foot. And so in a 1 megawatt hour battery design that is designed to last about 10 to 15 years, we're confident we can provide 10 megawatts of power. Um, and so how many racks does that extend to? How many IT rooms does that extend to? And so on in this disaggregated system. And so the whole point is power dense solutions. And in this case, near the uh, the the IT infrastructure that's drawing this power. I think in an ideal world, this would still leverage not necessarily a BBU, but maybe a CBU directly at the rack, to where we still have that peak load shaving right there at that immediate point near the GPUs. But the UPS kind of takes over for the BBUs, removes that requirement on the rack, allows that to be put towards more productive measures, and allows the high power UPS to really take kind of that forefront into long-term power and power and that resiliency side of things. And obviously this has a huge impact on frequency regulation as well. To put that into perspective, though, um, this solution compared to lead acid would be about 1/10 the footprint of a lead acid solution and about 1/3 the footprint of even the more advanced lithium ion solutions that I've seen out there on the market. So again, really power dense solution for frequency regulation and all those things. A lot of this has been supported by OCP's own work. Recently there was a presentation that went out on 800 volt, computing and what that's going to look like. Rack and Power Group and the Power Distribution Group are all working on similar models like this. And as you begin to transition lower and lower into these models, you see this more closely aligned with what I'm presenting today. Um, Things like the BBU and everything from earlier, allow us to do some early adoption, while also looking towards the future here in later stages. And then as we kind of move to the last part of this, um, I want to look at shifting energy storage to meet the needs of AI. And this is specifically, if you're in the battery world, this ESS specifically means like container units that usually sit outside the facility. And these are large battery storage units. Think of them sometimes as backup generators, or in this case, oftentimes they're supplying power long enough for the backup generators to actually come online. Um, and this was the question that really got us started down the whole story, and the one that I shared with you at the very beginning of the presentation, where they said, how much, what could we do if we had a requirement for 100 megawatts for about 10 minutes? what would that look like in terms of your footprint and cost and compared to other technologies that are out there today? And as we look at that table below, you can see kind of this stark contrast. You know, the power per container unit is a 12.5x difference. The number of units required on site is again, it's like it's more than 10 to 1. Um, Same thing with space claim. Um, the risk of thermal event is very low, and then the total cost all in is one half. So tremendous ROI, um, for data centers and AI solutions to look at a power focused ESS solution, and as they move forward. And to wrap up, I just kind of wanted to do a quick evaluation of the numbers. I think it's important. If we look at the amount of power that's consumed by AI data centers today, it's like 4% of our entire grid. Our today's grid is about 172 terawatt hours, so not a small amount. Um, a 1% in efficiency gain, is still huge. Actually, I'm sorry, that was I think yeah, it says AI data centers. I'm sorry, our grid actually produces 4.3, I think, petawatt hours. It's nuts. It's crazy. But we're 4% of that, so 172. But the 1% efficiency gain, correlates to basically just shy of 150 million based on the average energy cost, across the states for AI centers. And as we look at scaling this problem, we're expected to double the energy required by AI by 2030. Some projections are even more aggressive than that. And to summarize that, if we look at some of the energy efficiency gains that can be created through energy storage solutions, we believe all in, and this is a bit of a synergistic effect with high voltage DC architectures and everything, but there's potentially a 30 to 50% energy savings all in, that can be had at the data center level. Um, just in today, without even expanding into the future AI data centers, that could equal around a $7 billion savings in energy. So pretty substantial. So with that, I just want to share just a little bit about Ekion. We were founded in 2017 as a spinoff for Cambridge University. We're based in Cambridge, UK. And our focus is on novel high performance battery chemistry development, where we focus specifically on niobium-based anode materials. We have 60 employees covering, Europe, US, Asia, Australia, and Latin America. And we do provide battery solutions across the entire value chain through strategic partnerships. And so what that means is, yes, we do a lot of IP development and we create the chemistry, but we also have strategic partnerships and joint ventures with cell, module, and pack manufacturers, technology integrators, and even OEMs to help scale our technology to market quickly and make it easy for companies to say, look, we like this technology. How do we incorporate it into our solutions? If you're keen, if you want to watch some fun videos, a lot of our projects are under NDA, but we do have some YouTube videos out there, including the one in that QR code that's really fun. It's kind of done in a retro style. That's for a specific project that we actually had for mining, and fast charging vehicles. And that's it. I guess my call to action is, I would love to see a collaborative work group put together to kind of explore the benefits of power-focused energy solutions, to shape a little bit more of a sustainable AI ecosystem focused on energy efficiency, impact to grid, and benefits to high voltage disaggregated solutions. So, Alex, that's it for my side, bud.
Tyler, thanks so much. I really appreciate it. Um, eh, Super impressive outputs that you presented at the end, and I guess sort of putting on my day job hat for a second, I was interested to hear sort of who you work with, who you partner with, and would like to find more opportunities to connect you within OCP, maybe data center facilities, but also thinking like, would you be willing to meet with our battery folks and our UPS folks at Schneider just to talk about the chemistry and potential ways we could work together. Not to
Yeah,
sidebar this, I know we're supposed to only talk OCP here, but we're both OCP members, and we can figure out ways to collaborate.
absolutely, absolutely. To, I mean, the simple answer is 100%. We love to work with OEMs and end users. We do a lot of energy studies. We do a lot of battery development programs. And so, for instance, if someone like Schneider approached us and said, "We'd love to understand a bit more about your chemistry," we have very, very high level specialists that can not only dive into the chemistry, but also get into cell design, solutions based, evaluations. Um, and even connect you with our cell partners and everything if there was an interest in saying, hey, we would like to trial product and figure out what that would look like and everything. Um, so yes, we're very flexible. We're very horizontal in our business nature, and the whole point is to help industries find solutions to complex problems.
Yeah, absolutely. Um, Sadas, do you want to give voice to your question?
Sure, sure. So we have an effort in which we are looking at data centers here in Slack and Stanford. So the question I had was, are you looking at static loads in data center versus dynamic? I thought you are looking at dynamic, but your slides went by a little too fast, and I just couldn't catch that. So
Yeah,
the earlier one. No, even before there you had
this
even
one
before.
or
Yeah, I think one more slide before this or something. Yeah, this one.
yeah, yeah. So we are looking at we're looking specifically at dynamic loads. Static loads are fine. Um, I think we can just build power plants if we want to handle a lot of static loads.
Mhm.
Because I'll never forget one of the very first courses I did back in university was data analytics, and we talked about uh, nuclear power plants versus solar and wind versus peaking stations and all these different things. And one of the things that you quickly pick up on is solar and wind you can't control. Uh,
Mhm.
Nuclear is great, but it's very static. It doesn't like to go up or down very quickly. And then we rely on a lot of peaking stations and everything closer to the point of use, closer to that edge power case. And
Right.
we're asking a lot of those peaking stations right now. We're asking nuclear and other things like that to do things that they're not intended to do, which is respond quickly to dynamic changes. And then
Yeah.
solar and wind, those have their place, and I'm glad to have them, and I think we could definitely use more of them. But there's limits on those capabilities, and especially if you're looking at a kind of a steady state, 365-day, 24/7 operation, and like an AI data center.
So
And so
yeah, I was. Can you hear me or no?
yes, yeah.
Yes.
So I was asking dynamic from a different perspective. Dynamic in the sense of load that the data center is, because if it is AI based, AI itself has its own dynamic characteristics. So I'm wondering whether are you looking into that as well?
Yeah, I probably don't get into the level of detail,
Uh-huh.
that you're looking for on all of this. I specifically looked primarily at the GPU side of things.
Okay.
Um, and the biggest characteristics they had here is kind of getting into that software only mitigation, GPU
Right.
power smoothing. And and it was interesting as they said, on that software mitigation, they were like, for that we can they actually end up increasing other functions whenever the GPUs are in idle, to try to create a more, I guess, a better nominal energy profile that the grid is seeing
Mhm.
to the data center. But then you kind of wonder, it's like, well, do you really need that at that moment? Is that kind of a wasted effort or wasted energy, just because you want the power profile to look better? The other
Uh,
one was GPU smoothing, and that one there a number of different ways, including square wave, um, power smoothing and different stuff like that. But again, that has an effect on compute and
mhm,
how quickly we're responding. So nothing was ideal outside of that hardware case where you said, okay, what if we did energy storage and specifically made it with certain technologies? And that was very cyclical in nature looking at this study.
mhm, mhm. So these, when I look at the time constants, they are still in seconds. It seems to me, if I were to read your this with together with the energy source, the variations in the energy source, sustainable versus some other power source like natural gas, they
Well,
seem to be a lot more higher than this. Is that a fair summary?
Can you restate that one more time?
So if I look at the variations
Mhm.
of the load coming from the AI use compared to the variations coming from energy or power availability, the power or the power source or energy source seems to be a lot more higher variations than this.
Um, no, no. The supply
Am I reading it
is
right or no?
yeah. The supply is you're going to have your base load, and that's going to be, let's say, your large gas and coal-fired plants and nuclear. Nuclear being probably the ultimate base because it really does not like to think of it like a giant heating a giant brick. It takes a long time to heat up, takes a long time to slow down, to cool down. And so nuclear is very hard to increase up or down in a short period of time. Coal and natural gas both can respond more quickly, but they're especially the larger plants, they take a while. And then you have peaking stations, ESS, and other things out there in the grid that are a little bit faster to respond. But really, those are the exact word is respond. They are responding
Yeah.
to these
No.
very high frequency loads of that the AI data center is generating.
Okay, so my maybe another way of asking my question is the time constants. The AI load you are showing here is of the order of seconds.
Yeah, yeah. This is a
What is
small
the AI of the
snapshot.
Yeah, no, I understand. But even if I look across larger scale, it's still seconds, it seems. Um,
Yeah, I mean the some of the models that we had found, it was pretty big swings in power
Right.
because you're going into different training, or you're going into training models at different points of the day.
Okay.
And so the swings that were reported in multiple articles that we evaluated were tens of megawatt hours, hundreds of megawatt hours, even
Right.
even if it's just for seconds at a time, um, while things were waiting to respond and everything. And so that's what we based a lot of our analysis on. So
Okay.
if I'm not completely satisfying your question, though, feel free to send me an email, and I'd be happy to
Okay.
discuss it
I
further.
will. I will. I was still trying to pin it down quantitatively. So let's take it
Sure,
offline.
sure.
um, Catherine, would you also like to maybe verbalize your question?
Sure. Hi, hello. Thank you, Tyler, for the really good presentation. My name is Catherine from TDK Ventures. I think we already talked through the weekend. So my biggest question is, I think you also shared about BBU, CBU, and how they can combine together. I wonder what is the differences between, like, if you use alkaline cells and also compare with combining lithium-ion battery and supercaps together as a solution.
Yeah, this has been an area that we've really just started to look at. Um, we're not obviously like the CBU, I think has been offered by Delta. We certainly see the benefits in it. There's other partners like Skeleton that we've seen out there that have done these super capacitive based units. And we think it's really intriguing because there's a bit of a latency in battery power. It's not very much, but in a lithium ion battery solution, um, if you look at the course of milliseconds, it takes just a fraction for that power to be there, and that's where I think capacitive base units that it's nearly instant. And so as we look at this this kind of peak load support for GPUs, um, that instant power is really helpful. Um, the capacitive base units can only supply that for about 1 to 2 seconds, so it's not for very long, but it's immediate and it's very, very high power, high safety, and exceptionally long cycle life. So they can run through these high frequency type of reaction points, no problem for a very long period of time in a really valuable way that supports battery backup units, where those battery backup units are immediately there to respond for anything past that 1 second time, or potentially even top off the capacitive unit as soon as it gets past that threshold where it's now in the recovery stage, as opposed to the generation or the power phase. And I don't know if I answered your question, but the point is to have really two high power units working in synergy with one another, to create a
I see.
complementary environment.
So the Econ cells is not going to replace BBU or CBU. It will be put together with lithium-ion battery and supercaps.
Oh, no, no, no. Yeah, I'm sorry, I missed that second portion of it. The Exynos cells would replace the BBU. It would.
Oh, I see. So we'll replace the AMC batteries because they are not fast response enough, or
Yeah,
they're
we do.
great. Mhm.
Well, the BBUs today are they're fast enough to recover in 2 seconds, which is what the CBU would cover that first 2 seconds. The next important point, though, is how much power can you put out? Do you have a ultra high power cell that can do that at a high number of cycles? So, for instance, you can get a high power NMC or NCA based chemistry, but it can only do that high power cycle, let's say 500 times or 1,000 times. And after that, it's a compromised cell where you're going to have to pull out that rack to replace it. Um, in that same situation, our cells are currently testing at like 10,000 cycles, and even more, especially as you get into these small pulses. Um, we're expecting as we model this out, on an energy profile for a rack, it's about a 10, 15, even 20-year life. Um, and so that's the difference. It's much longer life under a much higher stress, higher power environment, and also adds an additional layer of safety, just due to the chemistry itself and some of the ways that that's formulated.
Got it. That's helpful. Probably one follow-up question is the power capability here, because when we say batteries, we see, we're talking about how many C rate, right? Are you talking about your cells can cycle for more than 10,000 cycles at like 20 C?
Yeah, yeah, there's some product out there on the market that shows 20C, using some of our chemistries, for well over 10,000 cycles. And we can develop, like for instance, if Schneider Electric approached us and they said, "Hey, we want to power base cells," and I'm going to bring that up just because Alex, mentioned their name earlier.
Fair enough.
We can, if they have a current cell partner, or if they want to develop their own cell, whatever it might be, we can work with them on formulation and everything to create a 30C or 40C battery, that can withstand that high cycle duty, and generate as little heat as possible. And so that's where our chemists, are really, really exceptional at helping bring product to market, very quickly, leveraging our partners.
Yeah, that's great. Yeah, because I think I shared it before because we also make high power like LFP cells. I think it will
Mhm.
be good combination of two.
Absolutely.
Yeah.
Absolutely.
Thank you, Tyler. Really nice presentation. I've learned a lot.
Oh, I appreciate it. I appreciate it. Thank you for joining.
Thank you.
Other questions for Tyler? Hamid, you asked which OCP committees are concerned with batteries. I don't know if anyone else on the phone has a thought on this, or whether Shruti has joined us yet. My first thought is data center facilities, maybe power distribution within data center facilities, but I'm not sure, honestly. So I'll take that as an action and see what working groups are engaged in these questions so that, first of all, I can connect you, Tyler, and anyone else on the phone who wants to get involved in battery-related discussions within OCP.
Yeah, that's fantastic. And I can partially answer that, even though I don't have the
Yeah,
connection. So
please.
I'd still love the plug, Alex. But I know power distribution is they're actually working on a white paper right now that's going to evaluate battery solutions in kind of this new high voltage DC architecture. And then I've seen a lot of articles on rack and within the rack and power group. Again, I'm not
Okay.
very connected to either of those groups, so um, it'd still be great to get an introduction
There's
there.
sort of a Venn diagram there between power distribution within data center facilities and rack and power. Um, but yeah, I think that's sort of where Bess lives. Um, any other or comments or questions from anyone on any OCP sustainability topic? Well, thanks everyone for joining, and look forward to seeing you next month. Our call will be at 8 a.m. Pacific, more aimed at Europe than our friends in APAC. But let's keep in touch with each other in the meantime, and I will follow up with some guidance on how to continue the discussions related to batteries.
Hey, Alex.
Yeah,
Sorry,
go
this
ahead.
is Hamed.
Yeah.
I had an audio issue. I raised my hand. I wanted to ask a
Oh,
follow-up
sorry, I
question
missed you, Hamid. Go ahead.
on the battery before Tyler goes. Is he gone?
No, no,
Oh,
I'm
no.
here.
Yeah.
Tyler's
Yeah.
here.
Hey, Tyler, I'm coming from automotive. So in the context of sustainability, material sourcing and emission are really critical. And here with high consumption rates and other uh, carbon footprint impact. I'm curious, based on what you know, which I don't know, and that's why I wanted to get more insight. How advanced are those teams looking into those uh, issues? Because power optimization is one thing in terms of energy consumption, but carbon footprint, scope 1 and 2 are different topics as well. And because I'm coming
Yeah.
from a material and system perspective, I was curious if there is an interest in that type of work.
Yeah, it absolutely is. And good question. It's not one that I get asked all too often. One of the things that we're actually pretty proud of is if you look at the carbon footprint of our technology, specifically our anode material, which is niobium based, it's a fairly minimal refinement process. Niobium is kind of this inert material. So it's non-toxic. It's one that really doesn't, as we look at uh, harsh chemicals and everything to refine it to get it to the point of purity needed for battery ready application. Um, all of that is a very low carbon process, a low energy process, and looks very favorable compared to graphite or other oxide-based chemistries on the market. So very sustainable battery. And there's also a really good story for second life applications due to the high safety of the battery. So as you use this for high power applications or high performance automotive, um, as you run to the end of the life of that ultra high, fringe type of application, these could easily be repurposed and reused in energy storage applications for homes or grid or something like that, and likely have another 10-year life without problems.
Great. Yeah, I'd love to be in touch, especially about the committee. If you don't mind, let's continue this offline.
Yeah. Please feel free to email me, and that goes to the entire group. Love to answer questions, love to connect. Yeah, please feel free to reach out on LinkedIn. Would love to meet more of the team.
But Taylor, I don't think there is one single group in OCB which deal with battery and battery backup. It's spread out in multiple groups.
Yeah, agreed. Agreed.
Seems that way, yeah.
So the rack, some group deal with racks, and so I can send you an email with some of the groups. Let me know which one
Thanks
you
for that.
think, yeah,
Yeah.
which one you think is really the most appropriate for what we are talking about.
We could
Yeah,
also
no,
discuss, taking up Tyler's call to action and starting a working group within data centers, within sustainability, um, looking at battery chemistries. But I think it's a good way it's a good idea to start with data center facilities, rack and power, see what work is already being done so that we can make sure that whatever we're doing is additive and complementary.
Yeah, I agree with you, Alex. Alex, we can start with what they got and then have a dedicated group focused on this one.
Well, I'm excited.
It's a big subject.
It's a
Battery is
big
a big
subject.
subject. Yeah.
And it's an exciting one, and I'm glad that there's so much energy and enthusiasm here. So thanks everybody for joining, and thanks for the discussion, and look forward to keeping it going.
Thank
Yeah.
you very much.
Catherine, I like your idea. We should just form a group.
Yeah, I agree. I agree too.
That's what OCP is all about.
Yeah, I agree with Alex. Good idea, Alex.
Well, good idea,
Yeah.
Hesham. Thanks
Thank
everybody.
you.
Have a good day. Have a good night. We'll talk soon.
Bye
Thank
bye.
you.
Bye
Take
bye.
care. Bye.
Cheers. Bye.